Hi ladies and gentlemen, I want to make a quick video that looks at the chain rule. So the chain rule is one of these things that gives students fits all the time. Eventually we kind of begin to be able to work through and calculate the derivatives correctly, but no one really bothers to explain why we have to do the chain rule in the first place. So what I want to do is just give you a simple intuitive example, hopefully that will help you understand why we are doing the chain rule. So what I have here is I have a room, and I'm going to say that this room is 120 feet. So it goes from 0 to 120, and I'm going to say that this axis is the P for position axis. This is position. Okay. And what we have is we have a temperature gradient through the room. We have a hot side and then we have a cold side. And so the temperature distribution in the room looks like this. The temperature is a function of position, and it's equal to 120 minus 2 times P. And we'll say that the position is in feet. That's fine. We'll say that the room's 120 feet long. So being able to find the rate of change of temperature in the room with respect to position is quite easy. We can take the derivative of T with respect to P, and of course that's just -2. We are losing 2 degrees for every foot that we go through the room. That makes perfect sense to us. But what we want to know is, as we walk through the room or jog through the room or sprint through the room, what is the rate of change of temperature with respect to time? So not so much position. We understand how it changes with position, but we want to understand how this temperature changes with respect to time. In this case, it makes a difference about how quickly we are moving through the room. If we're walking slowly, then the rate at which the temperature changes for us is different than if we run through the room, where the rate of change would be considerably faster. This whole idea is how the chain rule comes in. Let me give you an example. So let's take a look at a function, and this is not necessarily shown in all of its detail, but we're going to talk about it so that you understand what's happening, and it's a good precursor for substitution, integration by substitution, which we'll talk about near the end of class. So imagine for a minute that I have a function g of u, and this is equal to sine u. So if I ask you to find the derivative of g with respect to u, that's very easy. That is just cosine of u, no problem. All right, but what if u is a function of x? What if u is equal to x squared? And then I ask, what is the derivative of g with respect to x? Well, now it's not sufficient for us to just say, well, it's cosine of u, and then I substitute in for the u and I get cosine of x squared. That's actually incorrect. What I need to do for this derivative is I need to take the derivative of g with respect to x, and it's going to be the derivative of g with respect to u multiplied times the derivative of u with respect to x. And this is going to give us cosine of u multiplied times derivative of u with respect to x right here is going to give us 2x. Substituting for u is cosine of x squared times 2x. And this is the typical type of problem where you'll be using the chain rule. Now let me explain how this relates to our case of running through the room. If we want the derivative of temperature with respect to time, we want that rate of change, then we're going to have to take the derivative of t with respect to position, temperature with respect to position, multiplied times the derivative of our position with respect to time. And if you recall from physics, derivative of position with respect to time, this is velocity. And really it's not a vectorized quantity, so it's really the speed. But this matches with our intuition. the faster we run through the room from hot to cold, the more quickly the temperature is going to be changing. So let's say, for example, that we had, and let me scroll up a little bit here. Let's say that we had a position function which was equal to t squared over 4. So at time 0, we're at position 0. At time 2, call them seconds. After 2 seconds, we've moved 2 feet. After 4 seconds, right, so p of 2 is equal to 2, whereas p of 4 is equal to 16 divided by 4 is 4. P of 6, now we have 36 divided by 4 is 9. And P of 8, that would be 64 divided by 4 is 16 feet. So we're accelerating as we move through. And now we have something where we can calculate the rate of change of temperature with respect to time. So again, we have T of P is 120 minus 2 times, not X, but rather P. And then we have our P function right here. So when we take the derivative of T with respect to time, this is going to be our -2, which is the derivative of T with respect to P, multiplied times the derivative of P with respect to time. And that's going to be a -2 multiplied times T over 2. And that's going to be equal to -T. That is the rate at which the temperature changes as we move through the room. Now, you may be asking one more item. Well, can I just take this equation and do a substitution? Can I simply substitute in so that T becomes a function of T, and I have 120 minus 2 times T squared over 4, which would be 120 minus T squared over 2. Could I use this and then just directly calculate the derivative of temperature with respect to time? And the answer is absolutely. We can't always make substitutions, which is why we have the chain rule. But it works exactly the same. If I do this derivative, of course, I'll have -2t divided by 2, which is -t. And this matches with what we found over here. This is the chain rule, and this is the reason why we need to do this additional calculation is we have to account for the fact that we have this interface of multiple functions, and we have to take the product of the derivatives as we are calculating the rate of change. Thanks.